The time is now, okay, we're way beyond time. All right, so guys, I'm going to go through this final bit of final sequence of topics on reinforcement learning. So far, everything that we've done had to do with standard Markov decision processes and so on. Where the heck did neural networks come in? Why is this even being talked about in a neural network class, right? So we're going to try to deal with that very briefly. And quick recap, here's the story so far. We spoke about these general setups where you have a typical problem where you have some agent in an environment, the agent is in some state, the agent takes an action according to some policy, and in response to taking an action, the agent gets a reward. So, in our setup, if you wanted to actually have a real fly analog for our setup, you're going to have different swarms of flies on each edge. An action is to decide which edge the agent is going to follow. And so when the agent follows that action and he goes down the edge, the agent is going to get a reward which depends on the edge. But as a consequence of the agent's actions, the environment changes. All the swarms of flies are going to move. They're going to go to different places. And so the environment changes its state in response to the action. And our objective is to choose a policy to maximize the long-term return given how the environment actually changes its state in response to the action. So here's how we did it. We defined values. So let's start. So here's how we did it. So let's just think of a typical episode of what happens to the agent. The agent starts off in some state S1, takes an action A1, gets an immediate reward R2, but then the environment changes to state S2. So from S2, the agent takes another action A2, gets a reward R3, but then the environment changes to S3, and so on. And this happens. So the value of being in any particular state is the expected discounted return going all the way into the future. So that's how we defined it. And so and this is going to depend on the policy. So if the agent always moves left, if the spider always moves left, the flies will have one pattern of flying around. If the spider always moves downwards, the flies are going to have a different pattern of moving around. So the value of the state depends on the policy. If you're in a particular state where you always go down, a bad path, the value is going to be low. If you always follow a path which gives you more rewards, the value is going to be high. So our objective is to choose a policy that maximizes the return at every state. There were different settings. We have two different problems. If you're given a policy, how do you find the values of all the states or all the state action pairs? This we call prediction. Then how do you find the optimal policy? We call this control. Now this could be done under two different settings. In the first setting, you have a model of how the environment responds to an action at any state. We call that model-based planning. So this is where we actually had a proper Markov decision process where we knew how the environment changed in response to an action. And then you had the model-free setting where you really didn't have a clue how the environment was going to respond, but you had to learn about it anyways. So this one, we dealt with this using the Bellman. To find the prediction problem was dealt with using the Bellman expectation equation, where if you had any state, you took an action and got a reward. And then from there, you had a choice of different states that you could go to. And the value of any state was going to be, so the value of any state for a particular action was going to be the reward that you got plus the expected value in the future. And so the actual value of the state was the expected value for this guy discounted by gamma, and you took an expectation over the entire lot. So basically, what is the expected return going into the future? So you could similarly define something which was specific Now, if you thought of the state, then you would have to think about, you'd have to integrate over all possible actions. If more typically you thought of state action pairs, here's my pointer. Thank you. Let's watch out. So I've lost my clicker. Someone stole it. I'm left with my. Yes. Anyway, so the way we could either define the value for a state, in which case you had to integrate over all possible actions, or you could think of a state action pair and assign a value to a state action pair, in which case you just needed to know, to find the expected value of a state action pair, you need to know what the expected reward is over here and what the expected reward is downstream thereafter, right? So, and then we also saw the Bellman optimality equations, which is an iterative mechanism for finding the optimal policy at each state, right? So all these we've seen. And when we spoke of solving an MDP, you had two steps. Prediction: given a policy, you find the value functions, which could be either just the value or the action value function. And then you had control, where you had to find the optimal policy, for which we defined two different methods. One was the policy iteration, where we directly found the optimal policy. And then you had the value iteration, where you found the values under the optimal policy and derived the policy from it. So all of this we've already seen. And the last thing we saw was model-free reinforcement learning, where we actually didn't have any idea of how the environment was going to respond to our actions. And now this is the more typical situation in real life, that you take an action, the environment responds, you have no idea how it's going to respond, right? So going back to our Bellman equations, what this meant is that although we know what actions we can take, we may even be aware of what kinds of states the system has, what we don't know are those terms which are highlighted in yellow, which means it's quite impossible for us to learn either the state value or the value function or the action value function. And so, and still, although you don't know these transition probabilities, you are required to find the optimal policy. And that led us to model-free methods. Here again, we can think of two different problems. You still have a policy. The policy states what actions you're going to take with what probability in each state. So given a policy, how do you find the value of the policy? What do I mean by that? How do you find the value of each state? So how do you find the value function? Or how do you find the value of each state action pair? So how do you find the action value function, given the policy, but not knowing the underlying transition probabilities? So the way we did it, you actually run through the system. You land in the system. The spider lands on the cube, it begins wandering around. And each run, we will call an episode. And in each run, you're going to have a sequence of the kind that I've shown. You land on a state, you're going to take an action, you get a reward, but then the state changes. And so after several such episodes, we can actually use these to estimate the values or these state action values for the states. And again, to see how we would do this, we had several methods that we looked at. We had Monte Carlo methods and temporal difference methods. In Monte Carlo learning, we started off with this. For each episode, we started off running episodes. For each episode at each time, you could compute the return, which was a sum of the current reward and all the discounted future rewards. And then to find the value of any state, you basically averaged the returns at all instants in the episode where that state occurred. So here, for example, state SA occurs at time 1 and time 3. So to find an estimate for the value of the state SA, you take the average of G1 and G3. So this was the simple Monte Carlo based methods, and you could do the same thing for action value, state action pairs to find the action value function. Here the unit is going to be the combination of the state and the action. And so every time you basically identify all the instances where which the state action combination occurred and take the average of the returns at those instances to get the state action value. So this is easy enough. The problem, of course, is that this requires that you run the episode all the way to the end before you can begin computing things, because in order to compute the return at each time, you need the rewards all the way to the end of time. And it also tends to be noisy. Each time you run it, you're going to get a slightly different answer, or in fact, a rather different answer, right? So temporal difference learning sort of made this process more online and a little more stable. Now, temporal difference learning was based on a very simple concept. Now, look at this guy. So if I have, you take a state, you go to a state, you take an action, and as a result, you end up in a new state. You take another action, you end up in a new state, you take another action. This is a general sequence of operations that happens. And at each time, you're going to get a reward. And basically, what we are saying, what the Bellman equation says is that the value for the state is going to be the expected value of this reward and plus the value at this state, right? So you literally say the Vs is expectation of the reward at that time over all actions plus, in this case, the expected value of the future states. This is R. And if you actually have the answer, this equation is going to be perfectly valid, right? But if you don't have, and in this case, I can add Vs on both sides, and we add and subtract Vs, and nothing really changes, right? It's exactly the same equation. I haven't made any difference. I haven't made any change to the equation. So I can do this both for my value function and my action value function, and things are fine, right? So if I had the true value for the value function, this entire thing would hold, except that I don't really. So we're going to use this equation to update our estimates. And the way we do it is that assume that I actually have this guy. If I had this guy, which is the true value for the state at each time, then here's what I could do. This is going to be my true value for the state. This is my current estimate. At each time, from here, I can shift by alpha times the gap between the 2 points, which gives me a new estimate. Then from here, I can shift again by alpha times the remaining gap, which is going to give me a new point. And as you can see, this is guaranteed to converge, right? And so all we did was we just sort of switched it and said, OK, I have an equation that must hold. I can also rewrite it, being stupid that I am, I can rewrite it as an iterative process, which will give me the correct answer, except I'm not really being stupid. The situation here is that in real life, you don't really know what the true value is. So you can't just go up like so. So what we will do is that we'll replace this guy with the current estimate in the future. And so you're going to, and if you do that, you basically say maybe your current estimate for the expected value of the next state is off. So instead of your current estimate for the value, so here's what happens. You currently have an estimate for the value over here. But then, after having taken action, you see a reward, and you know that the value must be this reward plus the value at this state. So you're going to say, OK, whatever value I have over here that's off, I should really have been seeing something more like this, the sum of the next immediate reward and the value at the next state. And so now I can say this is how much I'm off by, which is going to be, so I can say this is how much I'm off by, the term within the parenthesis, which is the difference between the value that you would compute here, which is r plus the expected value of the future state minus the value of the current state, right? So this minus this gives you how much you're off by, which is going to give you an estimate of this gap, and you're going to take a small step, which is some fraction of that gap, getting closer to the estimate. So this is the standard TD estimate procedure. You can use this either for the value function or the action value function. And so the TD estimator was typically written like so. This, at each you would be running through an episode. At each point, you have an error, which I've written by delta, which is the difference between your updated idea of what you think the value must be based on the reward that you've just observed and the current value that you have for the state. And then you're going to correct the value for the state by some fraction of that error. Why a small fraction? Because you're actually just sampling. You don't fully believe what you just saw, you believe it a little bit, because this has been derived through in just one episode and not over infinite experience. And so here was the entire TD algorithm, where you initialized all the state values, you ran through many episodes, and at each episode, you basically, at each state, you computed this TD error, which was the difference between the updated value that you would expect that you think the state must have based on the reward that you just got, and the current value you've assigned to the state, and then you update the value for the state by adding a fraction of that term, right? So you can do the same thing with action values. That's all this line. But okay, so we've sort of seen how this kind of works, how we can now we can compute values for all the states, even if I don't really have a model. And the way I'm going to do it is, again, as I said, I'm going to run through episodes. I'm going to assign a value for all the states. And then at each state, when I go through the episode, I have some current value for the state. But as I run through the episode, I got a reward, but then the environment changed to some other state. And so the value for this state plus this reward gives me an idea of what the actual value for this guy must be, not what I currently have, but what the actual value for this guy must be. So I'm going to take a difference between the two and add it to the current value for the state to update my estimate for the state. I can keep doing this, and if I keep doing this, eventually I'm going to find over infinite time the value for every state. It's guaranteed that you'll eventually correct yourself to find the value for every state. But then what we are really interested in is not finding values for states. What we are really interested in is finding optimal policies. And so how can we actually extend this to find the optimal policy? We've learned how to estimate the state value functions, or the action for the MDP, which is the value function and the action value function for a given policy. Question is, how do we find the optimal policy? So this is the problem of optimal control. So you're going to have, and the way we would do it, we have a series of episodes of this kind as before, and so you can find the empirical returns at each time. The objective is to find the optimal action value function, Q star, for each state action pair. And ideally, we must do this online. So which means we never want to be at a loss for what this value is. We're going to have some estimate, and as we keep experiencing life, we keep waiting, and you don't wait until you die before you decide how good being at any place was. You keep updating your estimate for the values of the states and the state actions as you go through the episodes. So now we remember from previous classes, we actually had a way of doing this when you actually had a model for the environment. When you had a model for the environment, you started with any odd policy, and then you found the value function for that policy using the dynamic programming to iterations to compute the values for all the states. And then once you had the values for all the states, you could use these values to update your policy, estimate a new policy, saying, this would have been a better thing to do than what I started off doing. And then once you updated your policy, you use the updated policy to go back and estimate the values for all the states and repeated the process till you got a converged policy. So the question is, can we actually use this? Now, this was for a model-based formalism that we saw in previous classes. Can we do this for the model-free situation as well? And so here is the suggestion, that you start off with some policy and then let the world roll. And then once you've gone through several episodes, you can use this simple TD learning procedure that we just saw to estimate the values for all the state action pairs. And then once you estimated these values, you can go back and find the optimal policy by saying, at each state, I'm going to pick the action which resulted in the largest value. And you can repeat this process, right? So this is basically exactly the same as what we did over here, except now we're doing, instead of using the transition probabilities to find the action value functions, you're letting life go, and then you're using the episode, what you've observed in the episode, to find the action value functions. The problem is this doesn't quite work as advertised. And to see why, consider this very simple Gridworld example. So let's say you have a Gridworld example where you have some rewards. Actually, you have some penalties for wandering through the states. And the penalties are such that the optimal policy takes you like so. So it's the optimal policy takes you from the top right all the way to the top left and down bottom. That is the shortest way of getting to the terminal state, which costs you the least and gets you home most efficiently. But then you start off with a random policy. You don't know the optimal policy when you begin. So you start off with a random policy, you go through an episode. You have an episode of this kind, you have more and more episodes, and eventually after having run through several episodes, you go back and use the TD learning procedure we just saw to find the value for every state action pair. And having found the value for every state action pair, this is our action value function, we use that and we come up with an updated policy. Again, keep in mind, this is the optimal route, right? So you come up with an updated policy. And from these examples, you'll find that the updated policy looks like this, right? Now, using this updated policy, I'm going to go back and repeat the process again. I'm going to use the updated policy to repeat the process. What happens? At each state, you're going to be, because you've already chosen just a unique action at every state, at each state there's only one way to go. So every single episode is going to look exactly the same. And so when you go back and update your policy a second time, you're going to end up with the same policy as before, nothing changed. We didn't actually find the optimal policy. This is never going to change. You're pretty much stuck here. And why did this happen? This happens because when you do something greedy, when you just run through everything, you find your action values and choose the best action at each state, you're pretty much committed to whatever you estimated in your first run through the system. And you're never going to change from that. And so the fact that you really have to the top left corner is something that you will never ever discover because your updated policy will never take you to the top left corner. So we end up with the situation of exploration versus exploitation. We didn't spend a lot of time talking about this in the last class. I'm not going to spend much time on it now either, but just to give you an idea, what we will do is that, it's best understood here, instead of saying that my optimal policy, according to my first run, instead of saying that my best policy over here is to go left, I'm going to say that the best policy over there is to go left 90% of the time and down 10% of the time. So although my current action values say the best thing to do is to go left, I'm not going to believe it entirely. I'm going to leave a little probability to try other actions. And so if I do that, now what will happen is in my future runs, I won't end up doing exactly this. There will be some runs where I go to other states, to other corners. And as a result, now I have a better chance of actually finding the optimal policy. And so that's exactly what we will do. We will follow the current policy, the so-called best policy 1 minus epsilon of the time, which would be 90% in the example I just stated. And we're going to do something random the other 10% of the time, the other epsilon of the time. And that gave rise to the algorithm we called GLIE Monte Carlo, where you produce an episode, you just run through the system, and then having run through the system, you use TD learning to compute the action value function for every state action pair. And based on those, you came up with the epsilon greedy policy, where at each state, you suggested that the action that resulted in the largest value must be taken with some probability 1 minus alpha, where alpha is 1 minus epsilon, where epsilon is a small number. But you also try other policies with some non-zero probabilities. So this was the GLIE Monte Carlo algorithm, and it's guaranteed over time, if you spend sufficient time, that this will eventually find the optimal policy. And from this, now in the GLIE Monte Carlo method, at each time, you have to run the entire simulation, the entire episode, and at each time you have to compute the return, which is the current reward plus the discounted return all the way into the future. And so this is not quite online, so we came up with the online version of it, which we call SARSA, which is the state action reward state action. And in SARSA, it brings us right back to where I was out here, which is that you're going to go through an episode. You're going to go through an episode. You start off with some policy pi, which is random. And then you're at some state. You take some action A, you get a reward. But now the environment changes to a state S prime. And over here, you can hypothesize an action A prime. And so now what happens is this state action pair has a value. This state action pair has a value. So you have QSA, you have QS prime A prime. In between, you got this reward R, and so you would expect to see this relationship that the state action value for this state action pair is going to be this reward plus the action value for this state action pair. You won't actually see this happen, so you're going to take the difference between this and what you actually have. That gives you a real error, and you can use the error to go ahead and correct your state action value. So this just goes back. This looks once again like TD learning, except that this is TD learning with an immediate policy update. So as soon as you update your state action value, which is your action value function, you update your policy immediately, and you update your policy using an epsilon greedy method. So this is just SARSA is just TD learning with immediate policy update using an epsilon greedy procedure. So this was our SARSA algorithm. All of this we've already seen so far, right? So I'll skip through the next few slides. Now, so far so good. We haven't yet gotten into neural networks. We just talked about reinforcement learning and how you can learn about states and action values and learn an optimal policy even if you don't know how the environment is going to change with your actions. But now let's scale things up. So if I'm playing tic-tac-toe, how many states in the game? Anybody? Anthony? How many states in tic-tac-toe? 3 to the 9, right? Because each box can have a yeah. They're not all possible, but they're in the limit. They're 3 to the 9 states. So it's a very small number. That's my point, right? But then the moment we begin to go to blackgammon is a really small game, simple game. It's got 10 raised to 20 states. If you go to chess, it has 10 raised to 120 states. If you go to Go, you have 10 raised to 160 states. I may be off by a digit or two in the exponent, but really that's still a huge, impossibly huge numbers. There's no way you can actually explicitly compute the value for every state, leave alone every state action pair. So the way we spoke about values and action values, we were thinking of these literally in the form of a table, that I have a state, I can give you a value. I have a state action combination, I'm storing the value. This cannot be done when you scale up the problem. And particularly if the state is continuous valued, there's no way you're going to be able to do this, right? So if you have for example, even in our simple grid world, instead of saying you have to be in one of these 25 positions, if I allow x and y coordinates to be continuous, then there's no way you can actually store these values. There are infinite possible states. There's no way you can actually store these values or state action values in a table. So what we will do is to change this to a parameterized function. You're going to have a function f, and this function, if I feed it a state, I feed it an action, that's going to give me QSA. This function can be anything, right? Or you could do it differently. I feed it a state, and it simultaneously gives me QSA for all of my actions. They're just different variants of doing the same thing. But the point is, now you have an abstract function that actually gives you this action value for every state. And if I do this, this function is going to be parametric. So this function could be anything. And I'm going to, instead of learning the action values for every state action combination, I'm simply going to learn the parameters of this function. Now the way I will learn the parameters of this function, I can give it states and actions. It's going to give me some output O. I have the actual state action value for that state action combination. I can define a loss between the two, and I can learn the parameter theta to minimize this loss. Right? This would be the obvious thing to do, and the way you would do it is you can just use simple gradient descent. This is your loss function, and you take the derivative of the loss with respect to theta. You can just do a simple gradient descent. The problem, of course, is we don't know what the true state value is, but let's get to that. What kinds of functions can these be? It turns out these functions can be anything. The simplest one is to just define each state action combination by a huge feature vector. For example, in a chess game, I can say that the state action combination is a big 64-dimensional vector which has exactly which piece is in each of my boxes, or something even longer, where I represent the entire thing in binary. But the point is, this feature vector is going to be finite in size, and it's going to be very specific to the state action combination. And I can think of a weighted combination of all of these features to assign the state action value. Or alternately, coming back closer to where we are, I can just think of a neural network to do this. So for example, when you're playing chess, you're not really going to be enumerating things. Typically what they will do is just take a picture of the chessboard, you run a convolutional neural network over it, and the CNN is going to give you the state action value, right? You have a certain number of actions, that network. And so suddenly we've gone around and tied up the entire business of reinforcement learning with neural networks, where the neural network is now giving you the action value function. So problem, how am I going to train this neural network? I need this true Q value, right? If I don't have this true Q value, I cannot compute the loss. I cannot actually train the parameters of the network. So standard supervised learning is not going to be possible because our real problem was to estimate these guys in the first place, and we don't know what these are. So we are going to use bootstrapping. What is the bootstrapping? Now we go right back to our board. I'm going to run through my episode, and for each of these, so I have my state action values, which is going to be FSA semicolon theta. This guy gives me this value for this state action combination. I run through the episode. This guy also gives me this value for this state action combination. So this value over here, right? So now R plus gamma times this term, which has been obtained from my function, is giving me the target, what the value for this term must be. The difference between the two is giving me my error, and this error is basically my loss function. I can simply think of it as the absolute difference or the squared difference. The squared difference tends to be more amenable to mathematical tractability. And now that I have this difference, so this target over here is going to be this reward plus the state action value for this combination, where this action itself is chosen in a greedy manner or an epsilon greedy manner from here. And now I have my Q target, and now I can compute the difference, the divergence. The divergence is a function of theta, and I can do my derivative updates, right? So the gradient descent. So the whole thing works out just very cleanly, like so. Now, keep in mind that there are two things over here. So when I'm taking, where is the eraser? Let me draw this again, right? You had state, you had action, which gave you a state S prime. You had an action A prime, which you chose greedily from here. And you computed F S prime A prime, which is a function of theta. For this guy, you computed F S A, which is a function of theta. And you got a reward over here. This was your target. This is the current value. You're trying to estimate theta to minimize the difference between the two at each step. But here's the problem. Both this guy, which is in the target, and this term, which is the term that you're actually trying to learn, are functions of theta. And so directly optimizing this ends up being nasty. So what you will try to do is freeze this guy and say, I'm not going to take a derivative of this term with respect to theta. I'm just going to use the actual value that I got. And the only term whose derivative I'm going to take is this first term. So it's not really gradient descent. It's what they call semi-gradient descent. And this leads to the fact that you have the semi-gradient descent leads to various variants in the estimation procedure. So there are some limitations in this whole process. When you begin using functions, parameterized functions to learn values and action values, you end up with a business of limited capability. So what do I mean by this? So let's say you have a finite state space, or let's say you have this magical computer which can store very, very large tables, even for a chess game. Then, as I'm learning something while playing chess, if I've stored the action value for some state, when I update the action value for another state action combination, this guy is not going to change. So the updates are always local. Whatever state action value you're updating is the only one you're going to update when you're using a table, because things don't interact. But on the other hand, when you have a function, so what I mean by this is that if I update in a table, if I update this guy, this one is not going to change. But if I'm using a function, if I update the parameters to improve this one, because the same parameters are also being used here, this guy too is going to change. So you have a moving target. Your target itself changes as a result of your update procedure. And this ends up being a problem. So what does that mean? So what does that mean in tables versus functions? In tables versus functions, in tables, let's say I have a very large state space, and I use an epsilon greedy policy. Over enough time, I'm going to visit every state, and I'm going to learn the action value for every state action combination. So all I have to worry about is running things for enough time. How frequently I visit any state is not of relevance, because the update to one state doesn't affect the updates to other states. But then when I have a function of this kind, here's what happens. As I keep running through the process, even if I'm using an epsilon greedy policy, I'm going to visit some states less frequently and other states more frequently. And the states that I visit more frequently are going to cause the greatest influence on my parameters. And so because they are going to influence my parameters, when I keep updating, say, state 7 repeatedly, I'm going to update my parameters to optimize it for state 7. Because I have a finite set of parameters, as a consequence, I'm going to make it worse for state 3, which I haven't really seen in a long time. So even if I keep going through the process, if I visit state 3 infrequently and visit state 7 very frequently, just the fact that the two have different frequencies is going to result in poor estimate of the policy at state 3 or of the action value at state 3. So having problems such as these means that you can't just use this process as is. It will give you poor estimates. So there are various solutions that have been proposed. I'll just sort of touch on a couple, and I won't spend much more time than that. So one of them is action replay. And in action replay, what you will do is you're going to go through your episode. You're going to go through your episode as A, S, A, S, A. And each of these, having run through the episode, you're just storing all of these segments in a buffer in your memory. You don't begin updating things immediately. And then afterwards, you sort of randomly sample these little sequences that you visited from your memory. And then use those sequences in this update rule right here to update your parameters. It's something that they call action replay. So one of the benefits here is that you don't have to keep playing the game repeatedly. You don't have to keep running many episodes. If you visited some low probability state at some point in some episode, you can go back and resample your memory to make sure that you actually go back and re-update the parameters for those states, and don't forget about them. So this is pseudocode for action replay. Now there's a second mechanism that's often used, which is that, see this term here? This is part of your target. This is what you're trying to estimate. And in the standard format, both of them are being computed using the same network. Instead, you will have two networks, N1 and N2. You keep N2 fixed, and N2 is going to be computing these target values every time, and N1 is what you keep updating. So after a while, N1 sort of learns to look like N2, then you flip the two, and then repeat the process. And so that way, you get rid of this business that the target keeps moving, that when you update the first guy, the second guy changes too. So these are all different variants on the basic Q-learning mechanism, which are ensured to make sure that the whole process of training is somewhat stable. Right. So what we've seen so far is we actually have no reason to be looking at this slide. It's just there for because from a paper many years ago, like 3 years ago. These days, of course, you have AlphaZero, and this is from when you had things like breakout. But what we've seen so far is a mechanism which allows you to estimate a function learn this function, you can determine a policy. At any state, you can just find the action which results in the highest state action value, and that is going to be your policy at that state. The problem with this approach is that the number of actions is very large, or if the number of actions is itself, the actions are themselves continuous, like the amount by which you might turn, for instance, then enumerating the state action values for every action and picking the largest one is going to become infeasible. So you can't really use action value functions to decide your policy. It's going to be computationally intractable, or at least infeasible. So in these cases, what you want is something better. You want something that actually directly gives you the policy. It says if you're in state X, here's what you're supposed to be doing. And so in that case, we end up with direct policy estimation, which is also a deep neural network in our case. But what it does is to actually give you policy values. It gives you a policy function, which gives you a probability distribution over actions. So this probability distribution, in the explanations that I've got, I'm assuming that the number of actions is actually finite, and so countable. And so you actually get a probability distribution over the actions, but you could use the same mechanism for situations where the number of actions the actions are continuous, and this function can actually give you the parameters of a continuous probability distribution over actions. Regardless, the point is now we have a function f which at any given state will give you a probability distribution over actions. And this function f is also parametric, and it must be learned. So here you're going to have a situation of this kind. You have s going in. It's going to give you probabilities of all the actions. Or alternately, you have s going in. It's going to give you some other parameters theta prime, like the mean and the variance of a Gaussian, and the output of that guy, or the second function, is actually going to be a probability distribution function. So regardless, you have this function f, which is parametric, which takes in a state and gives you probabilities for the various actions. And you want to learn this function such that it gives you probabilities such that it gives you a policy that maximizes your expected return. So in other words, you want to learn the optimal policy, and the optimal which means you want to learn the optimal policy function f. Now there's a problem here, that in the case of the policy you really don't know. In the case of the value function, in the case of when you're trying to estimate the value function, you could imagine that you had the true values for every state action pair. So you have the actual action value function, and then you have this approximator, and you are trying to minimize the loss between the true values and what the approximator actually gave you. And the true value was your target, and what the network gave you was the estimate. And if you minimize this loss, eventually you got a network that was really good at estimating action value functions. But when you're trying to optimize the policy, you have a different problem. So the policy is about actions. We don't really have a golden action sequence. You can't imagine that you have a known golden action sequence that you can minimize the loss with respect to. Also, the policy may not be unique. There may be many optimal policies. There's no way of defining a golden truth against which you can compute the loss. You have to think about things differently when you're speaking of policies. And the way you think about it is literally what the point of the policy is. The point of the policy is to maximize, the point of finding the optimal policy is to maximize the expected return. So at each state, there are many actions you can take. Each of those actions, so if you're at any particular state, S, you take an action A1, you end up in some state. You take an action A2, you end up in a completely different state, right? You take an action A3, you end up in a completely different state. And you're going to get a reward in each one of these guys. So each of these states is going to have a different value to it. And what you really want to do is to choose the action where the sum of these two guys can be expected to be the largest possible, right? So you literally want to say, find me my function f such that if I use that function to choose my action, the resulting reward, the resulting return is going to be the largest. Problem: you want to find a function to optimize a choice. Choice is not a differentiable operation. We saw this in homework 4, right? Anytime you're selecting something from the output to feed it back to the input, it's not differentiable. That's where the whole business of softmax and Gumbel noise and all the rest of that came in, right? Choice is not a differentiable action. So operation. So the return is not differentiable, and you can't really use simple differentiation to optimize this function f, which is your policy function. There's also a second term. The first is the fact is that you need to choose, and choice is not differentiable, but even the choice is based on knowledge of the values at the subsequent state, which you don't know, right? So there are two different issues coming in simultaneously. One is that our policy function cannot be directly optimized by differentiation, and the second is that even if it could, it requires knowledge of terms that we don't really have. And so there are a couple of different solutions for this. The first one deals with the fact that differentiation is not, that selection is not a differentiable operation. So we recast differentiation as an expectation operation. This sounds odd, but it turns out that in this particular context, differentiation is actually an expectation operator. The second, so that takes care of this business of selection. And the second, we don't know the value over here, we'll estimate it. And we'll estimate it using a different function, right? So this gives rise to two different classes of solutions. The first one is the simple policy gradient method. The second is what we will call actor-critic methods. And we'll see how that works. Let's look at policy gradient methods as a first cut. So here is how we want to choose a policy. Let's say you're running through an episode. You start off at some state S, then you have some initial policy, and based on the initial policy, you choose actions. So you take some action, the environment changes, you have a new state. You take another action, the environment changes, you have another state. This happens for a while. So at the end of this run, you have an episode of the kind you have there. This episode really comprises of two components. The first is the sequence of states and actions. You were at some state, you took an action. The environment changed, you were at some other state, you took another action. So this is what we'll call our trajectory, the sequence of states and actions. This is what was actually followed. The second is the sequence of rewards. That's what you got back from the process, right? So you can separate the thing into the trajectory T and the total reward or the return, which is more appropriate. So if you think of it as starting from a state S, the return that you got for using that policy from state S. So you can decompose this into two terms. One is the trajectory, the other is the return that you got from that state. Now the choice of the parameter f, so because the policy is being given by the current policy network, the trajectory depends on theta, right? So the choice of the parameter theta will modify both the trajectory and, as a result, the return. So you can think of it this way. At each state, you're going to choose an action according to your function f, but that's good. But the environment is going to change as a result of your action. But the manner in which the environment changed was also a function of f, a function of theta, because the action that caused it to change was a function of theta. So the entire trajectory is now a function of the parameter theta. Now the return, not the probability of a return. So the return for any particular trajectory is just a function of the trajectory. If at any state you took an action, you got a reward. This had nothing to do with the theta itself. If I give you the states and the actions, you get a reward. So the return itself is just a function of the trajectory. It's not a function of the parameter. So what we really want to do is to maximize the expected returns, which is to say you're going to take the average over all trajectories of the return for that trajectory. The expected value over all trajectories of the return for the trajectory. So I can define my objective function now, j of theta, which is the function of my parameter theta, which is the expected return over all trajectories, where the probability of any trajectory is a function of f, right? So once I have a function of this kind, how do I optimize it with respect to theta? Very simple. I can do gradient ascent. I have an initial estimate theta. I can differentiate this with respect to theta. I can take now this is different from standard loss minimization. Remember, when you're training networks, usually you minimize a loss, so you're doing a gradient descent. Here you're maximizing the return, you're going to be doing a gradient ascent. And so all I need to do is to be able to compute the derivative of this function g of theta. The problem again is that this term over here is a function of f, and as we saw earlier, because the action space is discrete, what this means is that a small change in theta, suppose I have a particular policy and I choose an action. Now the actions are discrete. So if I modify my parameter theta a little bit, will the action change? Very unlikely, right? Small changes in your parameter theta are not going to result in a change in action. You need to have a sufficiently large change in theta such that the most likely action changes, and now you choose a different action. So that you can't really take a derivative of the action with respect to theta, which in turn means that I can't really take a derivative of p of t theta, right? So here's what is going to happen. We're going to try to take a derivative of this expectation with respect to theta, but we're going to manipulate things slightly so that instead of having to sum over an exponential number of trajectories and explicitly computing the probability of each of these trajectories, we break the things down and convert it to an expectation. Again, observe that the real problem here is, in addition to the non-differentiability, is that when you take an expectation, you're summing over infinite trajectories, and you can't really go through that summation and take a derivative. So instead, instead, here's what we'll do. When I take the derivative of j with respect to theta, only p is a function of theta, so it becomes the sum over all trajectories of the derivative of p with respect to theta times the return for that p. But then here's a little trick that's often used in machine learning. If I take the derivative of p with respect to theta, I can multiply and divide by p. So I can say the derivative of p with respect to theta is p times derivative of p divided by p, right? But the derivative of p divided by p is simply the derivative of log p. So this simply becomes p times derivative of log p. What did we gain by this? Nothing really, except that now this derivative term itself ends up becoming an expectation. And once the derivative becomes, because it's p times the derivative of log p times gt, which is simply the expectation of the derivative of log p times gt, right? So I've converted the objective function from being an expectation to making the derivative an expectation. And there's a little bit of, there's something weird out here that I'll get to when I actually get to the end of this sequence of slides. But one of the benefits of doing this is now, again, first, I still have to figure out what the log of the probability of a trajectory is, or the derivative of the log of the probability of a trajectory is, and that's easy enough. The probability of a trajectory is going to be the probability of the state times the probability of the action given the state times the probability of the next state given the previous state and action times the probability of the next action given the next state, and so on. So the probability of a trajectory is given up there, p of s1 times p of a1 given s1, which is just given by our function f, times p of s2 given s1 a1, times p of a2 given s2, which is also given by our function f. If I take a log of that, I end up with two terms. The first two terms are the contribution of the environment to the probability of the trajectory. The second term is what is being contributed by our policy, this guy. And so these are not a function of theta. When I take a derivative of log of p with respect to theta, I end up with just a derivative of the log of the function values at each time with respect to theta, right? So which gives me back that the derivative of my objective function with respect to theta is simply going to be the sum of the derivative of the log of the policy function computed at each time times the return over for the trajectory, right? So this is still an expectation. I still have to sum over infinite trajectories to get this right, except now, first, before I can, expectations we know can be approximated by sampling. I can sample an average, and sampling and averaging gives me a pretty good estimate for an expectation. So that's what we will do, except I'm going to take one more, we're going to make one more final modification. If you look at the first term, it's the expectation of the sum of the derivatives of many log probabilities over all time times the total return over the entire episode. Instead, we're going to say that we're going to change it slightly. We're going to say it's going to be the derivative with respect to theta of the log of the probability of the action times the return at that time. So the change is really very small, and it turns out it works better, but the arithmetic may seem kind of a bit thick at this point, but the mechanics are very simple. So here's what we do. You would start off with an episode, record an episode, and then at each time you can compute the return at that time. We know exactly how to compute the return. It's the current reward plus the discounted rewards all the way into the future. Then at each time using, so this episode we're going to start off with an initial policy function to which you can give a state, and it's going to give you the probability distribution over actions. So you're actually going to be using the current policy function to compute your episode. And once you do that, at each time now over the episode, using that function, you can actually compute the log of the probability of each state action combination using your function, right? So the next step would be to compute the log of these log probabilities at each time. And now that's your forward pass in your network. And now I have my my derivative with respect to theta, which is simply going to be the derivative of the log of each of those f's with respect to theta times the corresponding return averaged over the entire episode. And this derivative, of course, over here, if you were using a network, this derivative of log of f is something that you would compute using backprop, right? And then you have a very simple gradient update rule. So what we've done over here is to recast the business of learning the optimal policy in a continuous space, also as sampling and backpropagation. And it gives you the optimal, it should give you in the limit the optimal value function. It's actually like maximum likelihood. If you look at what the gradient looks like, it's the expected value of the log of a probability times some term, which is the same as the expected value or the derivative of the log of a probability times some term, which is the same as the derivative of the log of the probability raised to that term, which is basically the same as saying that I'm maximizing over all trajectories p of trajectory raised to g of trajectory. This is what we are actually maximizing. So that this actually ends up being a maximum likelihood estimator. And this has an issue that in our estimator it ends up looking like so. At each time you're actually maximizing the log of the probability of each action raised to the return at the time at which the action was taken, which is all very fine, but then this is a maximum likelihood estimator. What is it going to do? It's going to increase the probabilities of all state action combinations that you saw, and it's going to decrease the probabilities of all state action combinations that you didn't see. So this is your standard maximum likelihood estimator, where anytime you see something you increase its probability, right? Now this is not a very great thing to be doing, right? So why? Let's say you visited a state many times and you took different actions at different times. Some actions resulted in high returns, the other actions resulted in low returns. Simply because you took this action means you're going to raise the probability of both actions. That's not a great thing to be doing. What we want to do is that, even amongst the actions that we did visit, if the return was low, you want to reduce its probability. If the return was high, you want to increase its probability. So this shouldn't work like a standard maximum likelihood estimator. So you toss in an extra term. You subtract a bias term. From g of t, you subtract a bias, which is going to be the expected return of the state at which that particular action was taken. So if the actual observed return that you got was less than the expected value of the state, it means this was a bad action. So g of t minus vst is going to end up becoming negative. If the return was better than average, it's going to be a good action. So this difference, g minus v, is the advantage that you get from taking that particular action. You call this the advantage function, and what we'll actually optimize is this advantage function. And of course, for this you need v of s. Instead, the typical procedure is to approximate it by the average of the returns over all times. And this whole process gives us the so-called reinforce algorithm, which basically you go over entire episodes. You compute the returns at each time, compute the average return, subtract the average return from everything so that you get the advantages at each time, and then do the little computation that I just showed you on the slides preceding, right? So what we did was to see how we can modify expectation into a sampling procedure, and now we can actually learn policy gradient methods, a policy function. But then there was a second aspect to it, which was that you actually needed this Q function, right? And what we did so far was that we didn't actually compute the Q function. You ran entire episodes. If you run entire episodes, that means you have to run an episode till the end to compute a return in order to update your policies. And that turns out to be a horrible thing to be doing. So what we will do is to actually also estimate these guys. And now this gives us something called actor-critic methods. The actor-critic methods are, so what is the fundamental difference between actor-critic methods and policy gradient methods? So in the policy gradient method, let me go up here. I went through the entire episode, and having gone through the entire episode, I computed so I went through the entire episode, S, A, S, A, S, A, S, A. I got rewards. And at each time I computed the return. And to compute the return, I needed everything all the way into the future. I needed this reward plus gamma times this reward plus gamma squared times this reward, and so on. What we will do now instead is we will have one function f which computes the policy. We are going to simultaneously have a second function g which computes the action value functions. And as soon as you get to this, you're going to use the action value function to compute this action value, and just use a standard TD approach to compute the return. And now you can actually do the update. You can update your policy function online. So these are actor-critic methods. I won't actually go through them. We're quite out of time. But there's a whole class of actor-critic methods. And the state of the art in reinforcement learning using neural networks is various variants of actor-critic methods. There are many, many variants to the basic idea. Ideally, I should be spending a lot more time than this 40 minutes I just did on this topic. But the magic in catching up with the state of the art in something like alpha 0 is always going to be some kind of actor-critic method, which also have the benefit that even if your environment is changing, meaning your opponent, this system, changes its behavior dynamically, the whole process can keep learning. So this means that you're learning the policy for a game while playing the game, while also looking at past behavior. It's kind of really interesting. Anyway, I should ideally be saying questions. There's no one here. Everybody's asleep. I'll stop right here. There is a guest lecture on Wednesday. I want everybody to be here because that's a guest lecture. This is for those of you who might be watching. I'll post on Piazza. Mike Tarr, who's in the psychology department, who used to head the CNBC, I think, does excellent work on the neural basis of cognition, particularly from the perspective of vision. And he will be giving us a guest lecture on Wednesday. So I expect everybody here. Thank you.